What I'm going to do is give you a bit of an introduction to the space program, but something to keep in mind as we're going through this. I'm going to use some PowerPoint presentation. I do apologize. I don't run the equipment here. I just use it, but we normally can show it on a bigger screen, so I do apologize for something has not worked today, and I don't know why, but we couldn't seem to get it going. So I'll use some PowerPoint things to kind of tell you a little bit about it. But the important part about this, it's your time. And it's your chance to ask any questions, and I mean any questions. I always tell people, if you're bold enough to ask, I'm bold enough to answer. So don't hesitate to ask questions. I'll try and again tell you a little bit about the training that I went through. Try and link it to some of the things that you're going to get a chance to do as you go through your astronaut training experience. And you realize, just to put this in perspective, just go from start to finish in the real program's about 4 years, and you're going to do it in 4 hours. So it's going to be a little bit different, and I'll try to point out some of those things that will be unique, but also give you a chance to experience a lot of the types of things we do, and at least get a better acquaintance with the types of things. Interestingly enough, one of the other things that you'll really, I think, appreciate out of the session that you're going through today is, you know, it's high-tech stuff. It really is, and that's very, very important to it. But in addition to that, and this is overlooked a lot, but I think you'll see it as you go through the training program today, the coordination, the communication, the teamwork it takes to pull this together. And it's not just the people in the shuttle cockpit. You know, we have a crew of from 5 to 7 people inside the cockpit, all working together. And of course, we train together, and so we understand. You get to the point where you can almost finish each other's sentences. I mean, you really work a very, very intensive year of dedicated training to get to that point in time. So the coordination, the communication, the teamwork it takes to do that, not only in the cockpit, but also in mission control. So very, very closely linked to the people who are controlling you. We train together. Again, we do what we call a joint integrated simulations, where we get into the shuttle trainers. And some of you will get a chance to see this again from your training standpoint as well. Some of you will be in mission control, some of you will be in the cockpit. And it is a real exercise in teamwork to be able to pull that together. Very, very important part. And the communication, and we have just enough diversity in here that the communication could get to be a bit of a challenge, but that's real life too. So it is kind of an interesting aspect of doing that. Now, I think everybody knows the shuttle fleet has been retired, so we're going to train you on the shuttle, because that's right now that's the program that we're most familiar with until we get our next generation, and we'll talk a little bit more about that next generation as well. But train you in the shuttle program. The shuttle program has ended, the space program has not. In fact, the young lady that I walked in with, Angela, as I mentioned, she's applied for the astronaut program, and sometime, I think within the next 8 weeks or so, they should announce the next group of astronauts, and we'll see whether Angela gets selected. I personally hope she does. She's a very, very bright person and very, very capable. Points out too the criteria of getting selected for the program. You don't have to be in the military, and you don't have to be a pilot. That happens to be my background. But we've chosen equally about 50% military, 50% civilian, 50% pilots, 50% non-pilots. Everybody has to have at least a Bachelor of Science degree in a technical field. So a 4-year degree in a technical field, and there's no one technical field that's better than the others, as long as you stay in that. Now, why the technical field? It's a complex vehicle. As I talked to you a little bit about the shuttle, 2.5 million parts inside the cockpit, as you'll get to experience, over 2,500 switches and gauges. And you know, with that many moving parts, the chances that you're going to have a failure are actually quite high. And so we spend a lot of time inside that cockpit. Again, I mentioned we spend 4 hours at a time doing simulations, where you get inside real intensive workload. The simulation team throws problems at you, and the better you get, the more they throw at you. So they can always stay one step ahead. We don't overload you with that, but you'll get a chance to get a nodding acquaintance with that as you go through the program. So minimum Bachelor of Science degree as a pilot, you got to have 1,000 hours of single-seat jet time. The young Japanese man that was out there was asking me, because he's talked a little bit about difficulty of getting into aviation in Japan. You don't have to be a pilot. And he was also talking about career fields. There's no one career field that somehow would automatically qualify you. As long as you, again, technical degree. Now, if you are going to apply as a pilot, you do have to have 1,000 hours of tactical airplane time. So commercial airplane time doesn't count for that 1,000 hours of a single seat jet time. So pretty much that guarantees that the pilots are either in or will have been in the military at some point in time. So that's the background. My particular background, I was graduated from the Naval Academy, got to go to a graduate school courtesy of the military. I also went through test pilot school. So about 6,500 hours of flight time, degrees, advanced degrees in math and engineering. So that was, and a graduate test pilot school. So pretty broad background. Additionally, although this is kind of hit or miss, it wasn't necessarily critical. It certainly didn't hurt in the selection process. I did have over 500 hours of combat time in flying airplanes as well. So, and that, what did that lend to it? Well, you know, I think I was able to demonstrate that, you know, respond reasonably well during critical events taking place, which, again, is going to happen in the shuttle. You are going to have failures up there. We knew you will on any generation of spacecraft. So being able to respond to those emergency situations and maintain a cool head was an important part of it. So I did get to fly twice, once on Discovery, once on Atlantis. By the way, we STS-29, STS-38, for those who are familiar with the system, we use that nomenclature. STS stands for Space Transportation System. That really defines what the shuttle was designed to do. So we're not designed to go to the moon, not designed to go to Mars, but to go into what we call low Earth orbit. Surprisingly enough, because you know, people are like, well, I see the moon's what, about 240,000 miles away. How far do we go in the shuttle? Well, the highest we've ever been in the shuttle in terms of going into space, about 350 miles. And that was to deploy the Hubble Space Telescope. Average space station today is at about 225 miles in space. My second flight on board Atlantis, a unique flight, a Department of Defense classified mission. The Department of Defense no longer, after the first 10 years, no longer flew things on the shuttle, but a unique mission. We were the lowest space flight in orbit. We actually we're just up right around 100 miles. It's amazing what you can see with the improved with a telescope or something from 100 miles up, or telephoto lens looking back down. I can tell you we deployed a satellite on that flight. I just can't tell you what that satellite does. It's still classified after over 20 years, but kind of a unique mission. Now, I've already talked about you know, the training that you go through, and the training in the cockpit is only part of it. You pick up a lot of other information. You have to know some basic astronomy. We use why? Well, we use the stars to navigate by. It's a little bit more sophisticated than using a sextant and taking a sighting, but not much. We just use computers to help us do that. So knowing the nav stars and the constellations out there was important. Human physiology, what happens to the human body when you're up there in space. Some of the things are kind of trivial. Almost everybody gets space motion sickness. It's like getting seasick or airsick. The causes are somewhat different. Long-term effects, the longer you're in space, the more these things affect you. Something that everybody, again, for the long duration flights, the loss of muscle mass, your muscles atrophy. Think about it. You're up there in weightless conditions. You're not even fighting gravity like you're on Earth. And so we have learned over time to take some special considerations. Today on board the International Space Station, everybody on board the International Space Station must exercise a minimum of 2.5 hours a day. I mention that because we don't have showers up there. So at the end of your 2.5-hour workout, the best you can do is a towel off and do a sponge bath. So a little bit challenging up there. We'll talk some more about that. Well, in addition to all that kind of baseline stuff, learning some of the science that you may be doing aboard the space shuttle or the space station, you do then get into, and this is where you're going to really link up to it, getting inside the cockpit of the simulators and practicing training. Two different versions up here. The one in the upper left-hand corner here is going to be more like the simulator that we have out here on the floor. Again, 2.5 million parts on the vehicle, inside the cockpit, 2,500 switches and gauges, so incredibly complex. And keep in mind that you not only have to know how those things work when everything goes right, but the odds are 2.5 million parts. What's the odds of a failure? Almost certain. I mean, with 2.5 million parts. And in fact, if you look at any of the missions that we flew, we did have multiple failures on every mission. Just too many moving parts not to have a failure. So you have to be able to train for all those different contingencies. Now, we do have computers, and you're going to go, well, what do the computers do? Well, we actually let the computers do most of the flying. The only time we take over and fly manually are doing rendezvous missions and during the landing phase. But the rest of the time, ascent, computers are doing everything for us. We do train to take over in case the computers fail. We've had some computer failures, never to the extent that we actually had to take over and do it manually, but we do the landings manually, and we'll talk a little bit more about that. We did upgrade the system. I got to remember this was on the drawing boards in the early 1970s, so it reflects 1970s aviation technology. Upgraded in the 1990s to what's commonly called a glass cockpit. And you'll see this in most modern airliners today, extensive use of computers and that technology that's on board. So instead of 3 computer screens, we now have a total of 9 computer screens, or as NASA likes to call them, multifunction displays. Big improvement, but it also had a downside. The improvement was you had more information to deal with. The downside, you had more information to deal with. It got only more complex inside there. And again, even though the computers are doing the flying for you, all of the what we call systems management, managing those systems, particularly when you have failures, being able to recognize the failure, confirm it, and then take the appropriate action. That's what you spend a lot of time training for with the crew. And again, in the dynamics of flight, where you're lifting off with a 5 million pound vehicle, 7 million pounds of thrust, as you're clearing the top of the launch tower, you're already going 100 miles per hour, pushed back into your seat with 3 times the force of gravity. It's a very, very dynamic flight. You probably know this from watching on TV, but do you realize that 8.5 minutes after you light those solid rocket boosters, you're traveling 17,500 miles per hour, 200 miles in space, and actually about 8,000 miles downrange. So when we refer to dynamic flight phase, I think you'll understand why it's really dynamic. So a lot of training that goes into it. I got to do one of the more unique parts. We don't really have an exact parallel for training for the spacewalk. We do have what we call the zero gravity wall, where we allow you a bit of a simulation of the weightless conditions. It's rudimentary, but try it, enjoy it. It's kind of fun to do. I think you'll enjoy it. We use that getting into the spacesuits that we wear for the walk. This is the most physically demanding part of the training that we went through, and the reason why is those suits weigh about 350 pounds. And we train for it, what we call our neutral buoyancy laboratory, using the neutral buoyancy of the water. I wish we could do that for everybody here. That would be very, very interesting to do. It's also demanding. You may be neutrally buoyant in the water, the suit still weighs 350 pounds. If we train like we're going to fly, so if we're going to do an 8-hour spacewalk, we're going to spend 8 hours at a time in the neutral buoyancy laboratory practicing the exact same events. If you've ever watched what we do up there on the spacewalk, some people have compared it to the choreography of a fine ballet. And it really is. I mean, everything that you do is so planned out, so orchestrated, because the time is precious. Of course, working with that type of stuff in that weightless environment of space is somewhat difficult. Interesting enough, the training was more difficult than the actual spacewalk. Why? Come on, put your thinking caps on. This can't be a free ride. You're weightless. Yeah, you're weightless. So you've got 350 pounds mass, but no weight. So the actual spacewalk was a bit easier than the training for it. Now, training for weightless conditions, there are a variety of ways to do it, and this is our KC-135. I'm going to bring this up because there is a company out there called Zero Gravity Corporation that does sell rides on a similar type aircraft. It allows you to go up and do these parabolic arcs. And why do you do that? Well, as you go over the top of that arc, you actually get about 60 seconds of weightless conditions. Now that may not sound like much, but on our training flights we did 90 parabolas, so we got an hour and a half of now it wasn't constant because you can't maintain that arc for more than about 60, 75 seconds. And you do pay a penalty for it because at the bottom you dive down and do a 2G pull out to go back up and do that. Anybody know what we call this airplane, by the way? Have you ever heard the name, the Vomit Comet? Well, it earns it honestly. And interestingly enough, it's not the zero gravity over the top that tends to make people sick. It's the constant 2G pull out at the bottom. So when people went on that airplane, I used to consult with that company, and we'd always try and talk people into using anti-motion sickness drugs, better living through chemistry. And people would constantly say, no, I don't. I want to experience everything. I'm like, no, you don't. You really don't need to experience throwing up in weightless conditions. So, but very, very good training device that we've used through the field. Just to bring this up, virtual reality laboratory, looking for an inexpensive way to, again, kind of trick the mind using the computers and those special goggles and the gloves. You can see down here he's reaching out. He feels like he's throwing a switch up there, and so it was good. Another good way of being able to do a little bit more affordable training. Now this is a part that everybody's going to get a chance to do, not in the airplane, but in the computer simulations, which is where we start training for landing the vehicle. very, very different iteration than any pilots in here, by the way, commercial private pilots, or anybody have any airplane experience? Well, let me describe that briefly. When you're landing, I'm sure everybody's flown on an airliner at some point in time. When you're landing on a commercial airplane, you're coming down a fairly gentle, about a 3-degree glide slope, descending at about 1,500 feet per minute rate of descent, and landing about 125 miles per hour with your engines running. When you're coming in the shuttle, you got to remember, once you come back from space, you've exhausted all your fuel, so it's a glide. You have no power available on the airplane. So getting slow is not a good idea. Remember that during this simulation. And we're coming in 7 times steeper and 10 times faster than a commercial airliner. So 3-degree glide slope, 21-degree glide slope, 1,500 feet per minute rate of descent, 15,000 feet per minute rate of descent. Now, obviously, we couldn't take the orbiter out and practice touch and goes. So in addition to the computer simulations, and you're going to get to do the computer simulations, there's a little bit of a contest that goes along in there. By the way, for the young people in the crowd, the kids usually beat, unless there's a pilot in the crowd, the kids, because kids are more used to the video game. So parents, be careful. They will probably beat you at it. And you'll get a chance to do that. In addition to that, from the actually astronaut side, we wanted to have an airborne simulator. So we use something called the shuttle training aircraft. We take a Gulfstream 2, a business jet, and modify the cockpit so it looks just like the orbiter cockpit inside. Now, how do we make that airplane fly that incredibly, I described how a commercial airliner lands. Well, this is like a commercial airliner. In order to make it fly that incredibly steep approach, we take it up to 30,000 feet. That's generally where we take over and start flying the orbiter manually. Let the computers get us down to 30,000 feet, and then at 30,000 feet, we don't fully trust the computers. In order to make that airplane do that, we put both engines in full reverse thrust. That increases the drag on the airplane, allows you to fly that 21-degree glide slope. So every commander who's ever landed the orbiter, minimum 1,000 approaches and landings. And again, you'll get to do that in the computer simulation. It's a good simulation. You'll enjoy it. The only heads up I give you is it's real touchy controls. So, we used to always talk about this when you're a student pilot. Student pilots have a tendency to what we call kill snakes in the cockpit. Boom, 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 boom. That doesn't work. Little input, see what you do. You're going to have it's basically a task. You'll see a circle, and keep a dot centered in that circle. And if you make a big control input, it'll go completely off the screen, and you'll never get back. So put in a little bit, wait and see what happens, then make another correction. So gentle, gentle, gentle. Very, very careful approach, but very, very demanding part of the training. Talk a little bit about the vehicle itself. In the background, the big external tank held 550,000 gallons of liquid oxygen, liquid hydrogen. That was the fuel for the shuttle main engines. The tank was the only part that was not reusable. We actually carry that all the way to the edge of space, jettison it, make sure it tumbles and burns up as it re-enters the Earth's atmosphere. Incredible thing about that. 550,000 gallons of liquid oxygen, liquid hydrogen. We feed that into the engines at the rate of 10,000 gallons a second. So if you got a standard backyard swimming pool, you can empty that pool in about 2 seconds. Just to put things in perspective. On either side, the solid rocket boosters, those are the most powerful solid rocket motors ever built. They only burn for 2 minutes and 10 seconds. They're like big Roman candles, because once you light them, you're going. And you can't shut them off, and you can't throttle them. So it's full bore for 2 minutes and 10 seconds. That actually gets you above the densest part of the Earth's atmosphere. Then we jettison them off. Parachutes come out, they land in the ocean. We do recycle those, so we're able to use each of the solid rocket casings about a dozen times each. And then, of course, the orbiter vehicle itself, crew compartment up there at the top, 60-foot long payload bay, and the engine compartment back here. Any questions, by the way? I keep going. If somebody doesn't raise their hand, I just keep rattling along. Go ahead.
What were the things that failed on your missions?
Well, I'll talk about that a little bit. 3 minutes into the flight, we had an electrical power system malfunction. Now, here's what we saw in the cockpit. Again, you got to remember, you look at these gauges, you know, hundreds of hours of training. We saw a voltage fluctuation on one of our electrical sub-buses, which is an impending failure. It could be, and so and that's what you're trying to do. You're trying to catch it early enough. We called back down. Here's the way the conversation went, by the way. Houston Discovery, we see a voltage fluctuation on subbus AB1. Right back from Mission Control, Roger, Discovery. We see the same thing here on the ground. We think you're going to lose that system. Execute the emergency procedure. In less than 30 seconds, we identified the impending problem, confirmed it with the ground, and initiated the emergency action. The interesting part about this, why the overall complexity, our critical systems have 3 backups. So we can fail once, fail twice, still fly on the 3rd backup system. But again, it's the crew's responsibility to do it. That's what drives this intensive training program, that we had to be able to recognize that. Second flight, we had
So 3 minutes you're still going up.
Oh, you're accelerating at 3 times the force of gravity and pinned back into your seat. Yeah, it's not a trivial exercise. Fortunately, you won't have to go through all of that, but you'll get a chance to get a sense of it. In fact, I'll just give you a bit of a heads up on it too as well, because sometimes when we do the computer simulations for the landing, you'll get somebody who does real well because it's quiet and you're just sitting at a computer screen, and then you get inside basically the same exact setup in the cockpit, but things are going on around you. You've got other people in the cockpit, and there's noise, and somebody's trying to tell you this, and sometimes the person who's done real well with the landing gets so distracted. That's real world. You know, they lose track of what they're doing, and again, that's where the intensity of the training really helps, so that you can stay focused on the task at hand.
What was your job as an astronaut?
Both flights. I was selected as a pilot, but flew both flights as a mission specialist. So payload commander on one flight and flight engineer on the second flight. In fact, as it turns out, I was a little disappointed when I found out I wasn't going to actually get to, quote, fly the vehicle. It turns out, you don't fly it anyway. The only time you fly is during the landing phase, and the price you pay for that is that as the pilot and commander spend the vast majority of their time training for the launch and entry part of it. That's the most high workload times. The rest of the time, now I can literally say I've flown the shuttle, because on orbit you put a command into the autopilot, you push a button, and it does its thing, and you're okay. I've flown the orbiter. It's not a big deal. The interesting part for the mission specialist side is that the experiments are where it's all taking place, and as a payload commander, was intimately involved with the operations of the payload. So a lot more diversity, which I actually turned out I enjoyed more. I've never, it's a military model for training. Do it again, repetitious training, and I enjoyed the diversity a bit more. Lots of things. There is no exemption of things. Some of them trivial, some of them not. I'll talk a little bit about our waste management system. When that breaks, it's a big problem. You got to keep that plumbing humming. So there's a lot of challenges that are up there. We had to replace a computer on one of my flights. Something that the vehicle was never designed to do. Interesting enough, at the time it was on the drawing boards in the mid-1970s, nobody thought about in-flight maintenance. And later on, we found out that was the real secret to keeping it up as well as we could do this stuff. But it was never, since it was never designed for it. Some of the things like changing out a computer on orbit. The good news is, it's not like that 8.5 minutes getting to orbit. When you're on orbit, pace slows down, and you can work your way through, and you can keep. Hey, I can't seem to get a wrench on this bolt. Well, try a different wrench and see those kinds of things. So you can work your way through it, but not as time critical. The time critical part during that ascent phase is the most demanding part. Good question. Thanks. Anything else? Yes, sir.
What's the atmosphere in the cockpit when you're taking off?
Oh, good. Well, we actually use the same exact environment that you're breathing here on Earth. The difference is that unlike an airliner, have you ever noticed at the end of a flight how you've dried out and all that? It's because of the change in pressurization as you go up in an airliner. In the shuttle, we never change pressurization. We maintain 14.7 psi. So when we descended, how your ears pop coming back down, we didn't, because we never changed air pressure inside. So very, very comfortable, about 72 degrees Fahrenheit temperature, and very, very low humidity, 28% humidity on board. So very, very pleasant environment. Not, by the way, for crew comfort. That was primarily because it's an all-electric spacecraft, and you don't want water vapor up there. So that's the reason for that low humidity.
With the tanks, so the big one goes first, and then the 2 candles afterwards?
Well, no, actually, these
3?
only burn for 2 minutes and 10 seconds.
Yeah.
So as it gets above the densest part of the Earth's atmosphere, up to about 175,000 feet, and then we jettison them off, and then continue on with the tank and the orbiter.
With the main one, okay.
Yeah, you take the tank all the way to orbit. So we jettison up there. If there is any particulate left, which we never have found any, but it would actually come into drop into the Indian Ocean someplace. But no problems with it. Anything else? Good questions. Okay, from the crew standpoint, we did change a few things. Up until the time we had the Challenger accident, we used to launch in a cotton flight suit. This is comfortable but not safe. We realized we had to improve the safety. This is safe but not comfortable. It's like wearing a 90-pound wetsuit with all the gear on there, but it's a full pressure suit. And if you, as the Challenger crew did experience, we know enough about what happened in the cockpit that the crew actually probably survived the initial breakup of the vehicle, and actually may or may not have been alive when they hit the water, but could have been. And we decided we needed to improve crew safety, so the full pressure suit is a big help. You pay for it in comfort. It's, like I said, like a 90-pound wetsuit, so a bit uncomfortable from that standpoint, but an improvement, and we'll continue to have something like that. After an intensive year of training, come down here to the Cape. I'd gotten up about 3:30 in the morning for what was supposed to be an 8 o'clock launch. Get into our launch and entry suits, go on out to the pad, actually take an elevator up to what we call the 195-foot level, and then come over the orbiter access arm. You're going to be lucky. The orbiter out here is on horizontal, so it's going to be like getting into an airplane cockpit. Our cockpit was the same, but of course you're vertical for launch, so you've got to remember that you're sitting in a completely different orientation. So you're in an airliner type seat, but basically it'd be like taking the chairs you're in now, tilting them 90 degrees backwards. We're normally in that position for about 2.5 hours. Not so with my crew. We had a weather delay 15 minutes before our scheduled launch. They said the weather had moved in, and we're going to have to delay. My crew and I had a total of 6.5 hours in the back. Very, very fatiguing with that 90 pounds of gear on, and as I like to, not so jokingly, by the way, as I wish I hadn't had 2 cups of coffee for breakfast that morning. So that got to be a bit of an issue. But when you do go through the launch, and again, you'll see this in your simulation out here, at 29 seconds, everything goes on the computer. So nobody actually presses a button to launch it. It's all computer controlled. And the sensor suite in there is monitoring things within a few thousandths of a second. So, and proof of that is we actually had one flight, because at 6 seconds before the flight, you start lighting the shuttle engines. You light them in sequence, 1, 2, and 3. Actually had just initiated a sequence for ignition for the 3rd engine. The computer detected malfunction, shut it down. So less than a half a second before liftoff, the system worked. They felt, it wasn't my flight, fortunately, but they felt the engines rumble, and at that point in time, it's like, hey, we're on our, oh, we're not. Really, really disheartened. That same crew, by the way, had 5 different tries before they finally got off the pad. I can't imagine how frustrating they must have been, because after all that training and all that, then that's part of what you experience. It's the emotion, it's the anxiety, very, very human aspect to flying the vehicle. Not the least of which is, it's if we joke about the astronaut's prayer, please God, don't let me screw up. You don't want to make any mistakes while you're doing all this too. So a lot that goes into getting ready for the flight. When you get on orbit, those engines shut down as quickly as I can tell you about it. You reach your orbital velocity of 17,500 miles per hour. You're circumnavigating the globe every 90 minutes. 40 minutes of daylight, or 45 minutes of daylight, 45 minutes of darkness. It's something, intellectually you'll go like, oh yeah, that's right, but you probably haven't thought about it. You stop accelerating, because what you want is that 0 acceleration or weightless condition up there in space. And so when you're zipping around the Earth every 90 minutes at 25 times the speed of sound, you're literally coasting around the planet at that kind of speed. And of course, again, you want that weightless environment up there to do so much of the science they're doing. Yes, sir?
Do you have stability issues going on, or corrections as you go up?
No. The thrust pretty much takes over. We actually do, if you've ever seen a picture of the orbiter while it's still fairly low in the atmosphere, because once you're above 400,000 feet, you're above the atmosphere, you're a pure rocket at that point in time. We actually do load relief. So if you've ever seen the ailerons moving and everything like that, that's not for control, it's more for load relief. To avoid the bending moments and all that induced by the solid rocket booster. So pretty dynamic. The complexity of the vehicle is just absolutely incredible when you get down to it. Anything else? Of course, the best part of the flight is looking out the window. You're so busy up there. We plan on a 16-hour workday. Things never go as well as they'd like to. Usually ends up being about an 18-hour workday, so you're incredibly busy. But I'll tell you what, every chance, every second, if you can float over the window and look outside, that's the best play. Every so often somebody will ask me, do you take anything like video games? No, you can, but I can't imagine why. I mean, you really want to spend your time looking out the window. again, 90 minutes all the way around the globe. Get to see some 70 to 80% of the Earth's surface. In this case, Discovery is underneath the International Space Station. That's who took that picture.
What's it like sleeping in space? Does it affect the way that you can actually sleep?
I won't go into this. There's a lot of experiments up there. Everything from some medical experiments, some detailed experiments. One we called Chicks in Space. Took up some chicken embryos. One set that had been fertilized for 3 days. One set that had been fertilized for 9 days. Brought them back. The 9-day embryos all hatched. 3 8-day embryos all failed to hatch. So something in that spaceflight environment changed that developmental cycle. Those are the kind of questions you're going to want to answer for the future. I'm going to get to you. I'm not going to forget the sleep thing. I've got a slide that demonstrates that. Food is pretty good. A big change from the early days when they squeezed baby food out of tubes. Pretty good. Over 140 different menu items. In fact, an interesting spin-off. Anybody remember when the Chilean miners were trapped underground? We actually sent them some of our space food up there because it's all pre-packaged. It's either freeze-dried or thermally stabilized, and fairly compact packages, and was able to send it down those tubes they drilled down, and a nice variety, 140 things, menu items. The importance of that is, particularly for long duration space flights, the psychology of being, you having to eat the same thing all the time. It's boring, and it's at least an impression. So the variety of the menu items was a big aspect of that. We get pretty creative with it. Again, since we can't cook anything up there, we can heat things up, but not hot enough to destroy bacteria. So prepackaged, freeze-dried or thermally stabilized, heated up to make it more palatable, but edible, even if you can't do that. We also don't have a refrigerator up there, so we don't have any fresh food or any cold food up there. Get pretty creative with it, though. You can see here using the tortillas. Why tortillas? Regular white bread in that low humidity environment crumbles. And of course, anything that's floating around is going to be a pollutant in your environment. In fact, you see that when we talk about salt and pepper. I don't know what you thought about it, but how would you use salt and pepper? Well, we use liquid salt and pepper. Why? As long as there is moisture in the food, surface tension of fluid becomes an important property in the absence of gravity. And the example of that is when you release like if you take your water bottle and release water, it will always form a perfect sphere. I mean, an absolutely perfect sphere. And of course, everybody has to do this at least once every flight. You take your straw and you put it, you just suck it right out of midair. So kind of fun to do. Just guys play. Every astronaut's favorite food, turns out, was a shrimp cocktail or rehydratable shrimp cocktail. And I mention this because when I say rehydratable food, people tend to think of instant mashed potatoes or powdered scrambled eggs or something. No, we do better than that. Freeze-dried shrimp cocktail, I had 3 ounces of water. That may not look like much, but I'll tell you what, I've spent $10 or worse in restaurants. It was really pretty good. Sleeping, okay. 2 different ways of doing it. You can use the sleep restraints, as you can see my crew members doing it here. Now, on board the International Space Station, again, because of the longer duration flights, they actually have dedicated sleep compartments up there now. And what does that do? It gives you a degree of privacy. That's about it. So every crew member has their sleep compartment. You can put like personal photos and things. That's your home when you're up there. Why? You got to remember, whether you're right side up or upside down makes no difference at all. There's no gravity, so there's no difference in which orientation you sleep in. Most people do like to use these sleep restraints. The arms, that's just what we call neutral body posture, just where your muscles relax to in the weightlessness of space. Now, I'm one of a handful of crew members who didn't seem to mind free floating to sleep. Well, for one thing, I'm kind of a high energy person, and my flights are relatively short. And again, remember I said what I wanted to do was look out the window, and I also developed a habit someplace along the line. I can do just fine on an hour or 2 of sleep at night. So during our sleep period, I would float up on the flight deck, look out the window with my camera, and just marvel at the view. I mean, again, circumnavigating the globe every 90 minutes. Yes, sir.
Circumnavigating every 90 minutes. On Earth, you've got time zones and light affects your body's circadian rhythm. What happens with regards to space now that you've lost a 24-hour
Well,
life
actually,
cycle?
we do that, but we operate on what we call mission elapsed time. So there's no sense of trying to keep up with time zones. What most of us do, just for familiarity, is you'll wear a couple of watches, and one watch will be the mission elapsed time, the other watch will be like Houston So you maintain an association with a place on Earth, but you instantaneously adapt to it. It's like, okay, that was a 18-hour workday. It's sleep period. Going to go to sleep. 6 hours later, you wake up. Start that process all over again. Not an issue. Not an issue. The only time we did have an issue with it is when we didn't launch in the morning. And so on my second flight, we actually launched at about 8 o'clock at night. And you certainly didn't want to spend the preceding 12 hours awake getting to that. And so we did a based on some experiments they'd done at Harvard Medical School, where they found out that do you know how to adjust to your circadian rhythm, by the way?
Yeah, no, well, light.
Yeah, it's light. Yeah, well, I've heard for people who've traveled. Before I started doing all this sort of stuff, I'd always heard, well, you just you get on the schedule, you eat the right meal at the right time of day, and all that. It's nonsense. It has nothing to do with it. It's all exposure to broad spectrum light.
Yeah.
And so what we did is we had a room this size. They took it, covered everything in white beta cloth, so it was highly reflective. Took the entire ceiling, put in nothing but lights, and actually put in 3 extra air conditioners to handle the heat load. And then we'd sit there. It took us 3 days to adjust, and over 3 days, after increasing duration of exposures, after 3 days, we went to bed at 10 o'clock at night, feeling like it was, we went to bed at 8 o'clock in the morning, and felt like it was 10 o'clock at night, and just completely adjusted to it. And so that did help us then for the night launch, because if not, you'd been incredibly fatigued while you're up there. The question that everybody asks in the end, nobody really wants to talk about, how do you go to the bathroom in space? A quick lesson in human physiology. From the standpoint of the human body, all of our standard bodily functions, eating, chewing, swallowing, digesting, eliminating, your body all does that the same way in space as it does here on Earth. So we function just fine up there. The problem is the facility. You basically have a porta potty or chemical toilet without gravity. So you have to use airflow to do for you in space what gravity does for you here on Earth. So inside of what we call our waste management system, we actually have a mechanism that drives a fan that creates an airflow. It's hard to see it because it's right here in the picture. Urine collection device. And you just create an airflow through there. You urinate into the receptacle. The airflow entrains the liquid waste, carries it into wastewater tanks. Shuttle, we actually dump it in space. The International Space Station, what do we do with our wastewater?
Recycle.
Oh, we recycle it all for drinking water, yeah. And it's tested 6 times a day, and it's 100% pure, and it's tasteless, and you're okay until the first time you think about it. Then you're in trouble.
There's a shrimp off it.
Yeah. Solid waste collection is a little bit more problematic because in order to make it work, you've got to be firmly seated. And of course, normally in space, you don't sit. You don't have a reason to. You don't need to. Your body just adapts to whatever position you want to put it. Here, if you're not sitting, the airflow is not going to work. So we give you some help, some foot restraints and some thigh restraints. So you lock your feet into those foot restraints, sit down, hold those thigh restraints over your thighs, turn the airflow on, do what you came to do. My little cartoon, finish the paperwork. It's not the best part of spaceflight. We'll just leave it at that. Best part of spaceflight, again, looking out the window, flying over the Bahamas, the change of the water depth. Australia, the Great Barrier Reef is just fantastic from space. I mean, you can see all those colors. It's just absolutely incredible. No, you can't see the Great Wall of China from space. You can't see man-made structures. Geographical boundaries, rivers, you can tell, deserts, jungles, mountains, all that good stuff. Absolutely beautiful. And we really focused on that. Meteorological phenomena, volcanic eruption. Anybody remember a couple of years ago when air traffic in Northern Europe was shut down for a couple of weeks because of the Icelandic volcanoes? We do monitor those things and send data back to the ground. In this case, a very interesting phenomenon, the Aurora Borealis, Aurora Australis, exactly the same in the southern hemisphere. So pretty incredible stuff to look at. That's why you don't need video games. My favorite picture is the sunrise or sunset. I gave you a hint about this earlier on. You circumnavigate the globe every 90 minutes, 45 minutes of daylight, 45 minutes of darkness. You realize you see a sunrise and sunset every single orbit. So in any one 24-hour period of time, you're getting to see 16 sunrises and sunsets. It's absolutely incredible. I do like to point out, too, you see that band of color? That's the sunlight reflecting off the atmosphere. That is the 400,000 feet of sensible atmosphere that's out there. It's what keeps this planet lush and beautiful. And I'll tell you what, all of us who fly in space, astronauts and cosmonauts alike, you appreciate the beauty of this planet we live on, you appreciate what a fragile environment it is. So we all come back very, very much more interested in preserving that. When it's time to come back out over the Indian Ocean, we're going to get Don back into our launch and entry suits, fly the shuttle tail first, use the last of our orbital maneuvering system fuel to fire our engines. It slows us down. Laws of orbital mechanics are going to start to fall back towards the atmosphere. Now, falling, not flying. But once you start to hit the atmosphere, you start to gain control of the vehicle. But think about it, you're still at hypersonic speed, so over 17,000 miles per hour. As you start to encounter those air molecules, the friction of the air molecules on that hypersonic vehicle heats up the plasma or the air around the outside, somewhere between 2,800 and 3,400 degrees Fahrenheit. You can literally look outside, look at your wing, you see your wings glowing orange from the heat of re-entry, so absolutely incredible. Now in this case, just so nobody's confused, nobody actually, this is a wind tunnel depiction of the phenomenon. We're using a hypersonic wind tunnel, so it very, very accurately depicts the phenomenon, but nobody's actually out there taking that picture. You'll see this in your computer simulation. It's a 15,000 foot runway. Remember, you're in a glider, so don't aim for the end of the runway. Give yourself a little margin of error, about 2,500 feet down. And of course, you'll just be flying the vehicle by itself. We've never had any problem with that. We do use the drag chute as our primary deceleration device. Again, think about it, 225,000 pound airplane landing at 200 miles per hour. That's a lot of energy to put in those tires. And so to avoid any problems, we did put the drag chute into the program. Again, coming back after a relatively short duration flight, 45 minutes after landing, easy to walk off the vehicle. Again, not so with the people who've been up there for long term. And again, even with the exercise, it's still a little bit different getting your bearings.
How long was the flight?
My flights were 10 days.
Oh.
So and again, easy enough to 45 minutes after landing, I was perfectly comfortable. But again, if you're up there for 6 months, not so. The exercise helps a lot. We do have a protocol, by the way, when we come back, we have to rehydrate because your body loses
muscles.
So we do have to work on it. Of course, space station is still up there and continuing to be for another few years. Talked a little bit about the exercise using treadmill.
Did shuttles actually go up for 6 months at a time?
No, the shuttle was limited to about 16 days was the most that we could stay on orbit. We looked at extending that. We'd have to make some modifications. It just was never designed for the long duration. Ergometer. And something that's a little bit different, I talked about loss of muscle mass, also lose bone density. We measured as much as 18% loss of bone density up there. Tough to rebuild that. We'll call it's a resistive training device that has helped the bone density loss. So we've actually been able to cut that bone density loss at about half. We had planned on having a replacement for the shuttle by this time. It was canceled by the current administration, so back to the drawing boards. Now working on the space launch system. A big change that we've made, as you can see, obviously going away from the usable concept of the shuttle back to a Saturn V Apollo type configuration. And one of the big important changes, in addition to having a module instead of an orbiter, we're going to have a dedicated escape system. Now, the Russians have been using that for decades. We did not have it in the shuttle program. It would be a big enhancement. It will give you 100% crew survival. So very, very important. I've actually talked to the cosmonauts have used their system twice. I've talked to one of the cosmonauts who did. That's quite a fascinating story as the flames are coming up the side of the vehicle and they're waiting for the automatic system to fire them off, and it doesn't, and they finally manually pull the handle that fired them off. And quite exciting. They all survived. We're still in the developmental cycle of this, so whether we expect maybe first flight 2017, first humans on board in 2021. So we're a ways away from getting this system going. Perhaps the most exciting thing that's happening in the world of spaceflight today, and I truly mean this, it's going from the government sector into the private sector. And my analogy for this is aviation in the early 1900s. It started out as a government entity, eventually transitioned into the private sector. That's when we saw the tremendous growth in aviation. I think we're headed in that direction. A dozen different companies, Sierra Nevada, Boeing, SpaceX, Orbital Sciences, Bigelow Space. I mean, they're investing their own money. Why? Because there's a market. The last time I looked, there's a $2 billion a year market for researchers who want to do research in space. And so an incredible opportunity for private entrepreneurs. And I think once we get, the government will still do its thing and hopefully go back and do primary research, which is what it was designed to do, and then leave the operational stage up to the commercial entities. So with that, I know you're anxious to get going on your day, but I'd be happy to answer any questions. Go ahead.
Have you ever been on the space station?
No. Interesting, I'm very familiar with the space station. And when I left NASA after 10 years and got hired by the Boeing company, and I was the program manager for building the space station. So I know it quite well, but no, never did fly to it. Would have loved to. Fascinating, really fascinating. And it's international. Got to remember that. You know, a lot of different, 15 different countries that have contributed to building the space station up there. So very, very interesting. Yes, sir.
Did you ever get to go out of the shuttle?
Yeah, I did a spacewalk. I can't talk about it much. It was on that Department of Defense classified mission, so I don't go into a lot of details on what we did. Yes, I did. It's fascinating. End of story. I sometimes joke about it. Yeah, that was a secret mission, and it really was. I mean, it's still classified, quite honestly. Can you keep a secret? I can. So I'm not going to talk about it. They're serious about that. It was a very highly classified mission. We did take some pictures up there that I can talk about today. We happened to launch in November of 1990. That was during the build-up phase for the first Gulf War. The United States had retired all of its overhead reconnaissance airplanes, and they asked us to use our handheld cameras to take as many pictures as we could of Iraq and the Middle East. And we developed the photo imagery as well as the maps for Operation Desert Storm. So from a military standpoint, that was pretty neat. But for 5 years, I couldn't have told you that. That was all classified. The primary payload, the satellite we deployed, was still classified. And I don't think it will ever be released. Well, on top of everything else, it's still relevant technology. We're still relevant.
So it won't be a 50-year declassification?
Yeah, we'll see. We'll see. It'll be. I'll be dead and gone by the time.
Was that something that was done in conjunction with NPIC in Omaha?
No, actually, it was sponsored by the CIA.
Okay.
I couldn't used to tell you about that either, but now because we I sometimes something I just saw. Has anybody seen the movie Argo? By the way.
Yeah.
I just saw it for the first time here 3 weeks ago, and I was fascinated because at the end the guy talks about getting the intelligence award at the end of the mission. Well, we got the intelligence award for that, but they did the same thing to us. They marched us into the CIA director's office, pinned the medal on. I'm like, oh great, we're going to, no, took it back, put it in a vault for 5 years. There was 5 years that we could not even, other than it was obvious we'd flown the mission, anything we did was all classified. And they really take that stuff seriously. You don't mess around with it. You really don't. It was important. So. Anything else? Gosh, you guys are a good group. I'm sure you're ready to get going. I'm trying to figure out who's going to win the competition as far as the computer system. So, but if you'll be kind enough to go with Angela, we'll get you.